All right, I just recorded this video, or I thought I had, and it went like I didn't hit the record button. So you can see how much enthusiasm I'm about to have in recording this. So let's do this anyway. All right, so we have this shaft that is eccentric, meaning that somebody didn't install it right. It's not like rotating about the center of this wheel, this disc. It's off by the amount of E. It's also going to deflect enough so it's not rotating about the center, right? And it's deflecting because of this, by the way. But so instead of an R, because we use R for something else, let's make that X. All right. And just to give you like a little bit better of a look of this thing right here, this is the spot. We'll call that AB, where the shaft should be. Like, so that's the spot where the center of the rotation takes place. Here is the, let's say, here's the center where it's connected. So it is connected at the center of the thing, at least, well, not exactly. And then here's G. Okay, so it actually, maybe I should make it look a little bit more like that, right? So, well, yeah, maybe something more like that. Okay, so I'm changing my mind. Here's the AB where it's connected, right there. Here, or not connected, where it's spinning about. Here is where it's connected, right there. And then right here is G, where the center of the mass is going to be. All right, so what's interesting about this problem is we can use first principles with that kind of idea to get to the same equation as we would have plugging and chugging, so it's worthwhile. Also, I would note that if we were to draw from the side, I guess I could have drawn it this way right here. There's nothing stopping me from drawing it this way. And we draw it, right? Well, kind of like that. Well, didn't do the great job. Right there. Right, so here is, I guess, like that. All right. Here's where it's connected. Here's actually the center of mass right here. And here's the deflection. You could see a little bit better that right there is going to be what I'm going to call X, right? And they're saying it's got a stiffness that we could find from this if we were to look it up in the back of the book, back of a book. So knowing that the spring constant K is this right here, and we have an eccentricity, so we have an E, so that's going to be that guy right there. If I'm considering that the center of mass. We want to determine the angular velocity, omega f, at which the response will occur, all right? So which resonance will occur, not response. It's going to have response no matter what. And we also want to find the deflection R, but we decided X, let's call that X, of the thing in there at this particular frequency. So I'm going to get some things out of the way. Let's find natural frequency, square root of K over M. And so we have a square root of 40,000 over our 60 pounds. And we need to convert that to slugs with our 32.2. So we end up with 146.5 radians per second. And then let's convert our omega f, from 1200 RPM by multiplying by 2 pi and divided by 60, and we get 125.7 radians per second. And while we're at it, let's see what the ratio of these frequencies is going to be. And that ends up being something like 0. Let's write them out. No point in just taking shortcuts here. 125.7 divided by 146.5, and we end up with 0.8577. We've used black too long. Oh, let's go a little bit further. Okay, so these are just preliminary stuff that we could probably do right off the bat just to get there. But let me take a side step. Instead of doing the plugging and chugging thing, let's take a look at what's going on here with an FBD and an IBD. All right, so first off, what are the forces? Well, the forces are going to be related to this, right? It's going to be spring forces because it was mounted here, but now it's deflected there, so it's going to have a spring force that's going to be placed right in there, and that's going to be K times X. X being the distance the thing has moved from its center, right? It's going to be right in there, this distance that it's moved. And there's no other forces on this because it's vertical, so it doesn't have gravity. That's why they made it vertical. Over here on the other side, let's get some Christmas colors. We're going to, from the center of mass, which is this G right there, which I kind of placed a little too far off, but you can forgive me, right? That's going to be, it's going to be, if it's a constant speed, the only thing is going to be is normal acceleration. So it's going to be mass times the normal acceleration. And the normal acceleration is going to be about the center that it moves, right? So it's going to be this E plus the X times omega F squared. Right? A lot of times we'll call it R, but we use R for something else right here. So it's this, it's an eccentricity plus that right there. So you take the sum of the forces, let's call it the normal direction because it's the acceleration is the normal direction. And these two are aligned with each other, even though it look a little off. You get Kx is equal to me plus x omega f squared. Now we don't know x, so we can try to solve for it. Move it over to the other, this over to the other side. We'll distribute this, move it over to the other side. We'd get mx omega f squared is equal to m omega f squared. Oh, e. Sorry, e. Let me fix that. E. Well, separating out and solving for x, you get me omega f squared divided by k minus m omega f squared. And let's divide by k, the top and bottom. So you get e times m over k omega f squared. And you get 1 minus m over k omega f squared. And then you remember that the natural frequency squared is k over m. So we have that inverted, and so exciting. E times omega f squared over omega n squared. 1 minus omega f squared over omega n squared. And then lastly, we say that E times r squared over 1 minus r squared. We've now simplified this thing. And what we've essentially said, now something you should note is that this thing is mass of m, but it's also the mass that's off-centered, right, by amount of E. So if you go back to the equations that we introduced up here, you see that those two guys are equal to, let's get red going, equal to 1. We move him over, turn that into R, turn this into R. Note that there's no damping. And here we are. We got x is equal to E times, R squared. R squared divided by 1 minus R squared. Same equation right here that we would have had if we just done plugging and chugging. So let's go back to the problem. We were asking for the angular velocity at which resonance occurs. So duh, it happens when r is equal to 1, so therefore part A is a stupid question. Omega f is equal to omega n. I don't know why they asked it. And then now they're about the deflection when we're at 1200 RPM. Well, that's going to be when this happens when we're at that amount right there. So we're going to have x is equal to, oh, and by the way, notably, this is the only thing with any dimensions. So if we could just plug it in, we don't have, it's not going to, we don't need to convert anything right here. So we could just plug in E of 0.006 and plug in R 0.8577 squared, and then go 1 minus 0.8577 squared. And what we end up getting is 0.0167 inches. And that is the back of the book answer as well. Woohoo, yay! And there was much rejoicing. One last thing to note is we could have used a curve for this. Yes, this one. And we note that we had an R that was equal to 0.8577, right? So close to 0.855. Here's 0.5, so halfway through is 0.75. Halfway through in between those is 0.875, so just a little over to the side right here. Now we could also take a little ruler right here and do our very best to square it up. And go right here. Okay, so now it's a judgment call. They don't actually show, they only show 0.05 on here. Whoops, get back over here. They only show 0.05 on here. So, but making a judgment call without that being on there explicitly, let's just say it's 2.5 is about where it would run into the undamped curve had they included the undamped curve on there. So that comes with 3. So we have an input of 0.006, and we have this magnification factor that we apply to the thing of 3. And that comes out to 0.018, if I got it right. Boom. Right, so what was the answer? I'm just going to compare to 0.0167 inches. You can see that we got within the ballpark of this thing. That's like 0.017 compared to 0.018. It might as well be the same thing. And that was all about being like, I was just taking a ruler and looking at the thing. You could make, oh, okay, but it's a little bit different. Maybe it's a little bit lower. But anyway, that's the end of the video. And I'm tired of, I hope this time it recorded. Otherwise, it's just tough shit. Talk to you soon.